All right, you are welcome again. Today, let's talk about Bairstow's method. Bairstow's method. What is it talking about? Under numerical analysis, we are talking about how to solve polynomials, how to find the root of polynomials or transcendental equations. And we made a very clear introduction on this topic. We talked about methods for finding the root of polynomials. We made mention of direct method and we made mention of numerical method. And one of the numerical method that we mentioned is Bairstow's method. Okay, we made mention of Bairstow's method. So under Bairstow's method, we are going to take a comprehensive lesson on this topic, and I want you to pay attention because I strongly believe that before the end of this lesson, you should have a proper knowledge. You should have a proper information on how to solve any polynomial or any degree of polynomial using Bairstow's method. Yes, so that is what we want to talk about. Now, let me take you briefly on polynomials. You know that normal polynomial can be written as product of different polynomials like this. When we have p of x as a polynomial, it could be written as q of x multiplied by x minus a in bracket plus remainder. I think it's true, right? So when you multiply q of x, q of x is a polynomial, and then x minus a is also a polynomial. In this case, you can say it's a factor, then plus a remainder. Now, we see that in some cases, this remainder could be 0. It can be 0. So if remainder is 0 in this case, now that is to say that in this place we have x minus a. We see that a is a root of this polynomial p of x. I don't know if you get what we're trying to say. You remember when we talked about division of polynomials, we talked about factor theorem, we talk about remainder theorem. I think if you have followed us closely on that topic, a case like this, it should not give you problem. Now look at this. Let me use an instance to explain. Okay, for instance, let's see we have a polynomial p of x of degree 5 like this: x raised to the power 5 minus 8x raised to the power 4 minus 72 x cubed plus 382x squared plus 727x minus 2310. Okay, let's say you have something like this. Now we are saying that this same polynomial is the same as this one here. P of s is equal to, it has been reduced by the power of 1. So we have x raised to the power of 4 minus 6x cubed minus 84x squared plus 214x plus 1155 in bracket x minus 2 plus 0. Now we see that these two polynomials are equal, they are the same. But in this case, we see that x minus 2 is a factor of this p of x. Since it is a factor of this p of x, that is to say that 2 is the root of the p of x. That is, when you pass in 2 into this p of x, or when you find p of 2, is going to give you equal to 0. Hello. When we are talking about the root, we are talking about the solution or the value of a such that p of a will give you 0. Or we say the value of x such that p of x will give you 0. So here we say that x minus 2 is a factor of p of x. And at the same time, since we have remainder 0, 2 is a root of this p of x. Now let me show you something again. You see, this polynomial p of x can be written as this. This x minus 2 is a factor, right? It could be anything, maybe x minus 3. So x minus 3 is going to be like this. We're going to have remainder 960. We're going to have remainder what? 960, like this. So that means we have p of x is equal to x raised to the power of 4 minus 5x cubed minus 87x squared plus 121x plus 1090 in bracket x minus 3. So this is, it can be written like this. Then we have remainder 960. Okay, good. So now, this x minus 3 that we factored out, okay, it could be quadratic. It could be what? It could be quadratic. That is to say that p of x, a polynomial, can be written as product of two polynomials, of which one of the polynomials is what? Is quadratic, like this. Q of x is a polynomial multiplied by another polynomial that is what? Quadratic. Let's say x squared minus px minus q, then plus remainder. Okay, now you see that still using the same p of x, this remainder can also be 0, right? Good. Now let me show you something, a very clear instance what I'm talking about using this same p of x. We have x raised to the power of 5 minus 8x raised to the power of 4 minus 72x cubed plus 382x squared plus 727x minus 2310, right? Good. So this polynomial could be written as product of two polynomials, of which one of the polynomial is quadratic. It could be written like this: x cubed minus 9x squared minus 57x plus 385 in bracket x squared plus x minus 6 plus 0. Here you see that we splitted it into two, or we extracted extracted a quadratic polynomial from the p of x, and then you see here that the remainder is what? Is 0. Now look at this. We can solve for the root of this x cubed plus x minus 6, right? Now let me show you something. We are trying to find the root of polynomials. The root of what? Polynomials of any degree. You know how to solve degree 1, degree 2, that is quadratic and cubic, right? Good. We are talking about how you can solve for the root of polynomial of any degree. So now look at this polynomial p of x that we have is of degree 5. Now we started by saying that this polynomial of degree 5 can be splitted into two polynomials, product of two polynomials, of which one of them is what? Is quadratic. And now one of them is quadratic. This is polynomial of degree 5. When you extract quadratic from this polynomial, you are now having two polynomials, right? One is of degree 3 and one is of degree 2. You already know how to find the root of degree 2, which is quadratic. You can find it, right? Good. Then you also see how you can solve this polynomial of degree 3. But our major concern now is how we can extract this quadratic polynomial from any given polynomial of greater degree. Now let's go. You see, we can be using synthetic division for everything we are going to do. For the method of Bairstow and all of that, we'll be using synthetic division. And I'm very sure you know how to use synthetic division, but let me still give you a kind of a revision on synthetic division. Let's say, for instance, we cited example where we say p of x is equal to this, right? And then we have a factor, x minus 2, right? Good. So, when we say this p of x divided by x minus 2, okay, we are going to come up with another polynomial, right? So using synthetic division, look at it. Under synthetic division, when you want to use synthetic division, we use their coefficient of x, right? So arrange it on the table like this. Coefficient of x, we have 1, minus 8, minus 72, 382, 727, and minus 2310. Okay, and then here we have factor, right? X minus 2. All right, good. Or we say a divisor. So we equate this to 0. Now when we equate it to 0, we have what? X is equal to 2. Now that means we have p of 2. We have 2 by the side of this table. Then we bring down 1. This one multiplied by the p of x, which is 2, is going to give us 2. We write it under here. Then we add. Minus 8 plus 2 is going to give us minus 6. So the minus 6 we have multiplied by 2 up is going to give you what? Minus 12. Now add minus 72 plus minus 12 is going to give you minus 84. Now this minus 84 multiplied by p of 2, which is 2, multiplied by 2, right? It's going to give you minus 168. Now you add together, that is 382 minus 168 is going to give you 214. Now this 214 multiplied by the divisor, which is 2 up, right, is going to give you 428. Now you add together 727 plus 428 is going to give you 1155. Now 1155 multiplied by 2 up is going to give you what? 2310. Now we have minus 2310 plus 2310 is going to give you what? 0. Remember, we said it earlier, right? Good. So now we have the polynomial of degree 5 being divided by another polynomial of degree 1. So that means the quotient you are going to have is going to be reduced by 1 degree. So that means we are going to have our q of x, our quotient, to be what? We have the real polynomial to be degree 5. The degree now of the quotient is going to reduce by 1. So that means we're going to have x raised to the power of 4 minus 6x cubed minus 84x squared plus 214x plus 1155. Are we together? Yes. Now, I think we can also do this for 2 variables. We can also do this for what? For 2 variables. That is, you have a quadratic divisor. You have a polynomial and you want to divide it by a quadratic divisor. How can you do it? Look at it. Here, let's say for instance, we have p of x to be x raised to the x. So here we have p of x to be x raised to the power of 5 minus, we have this, right, to be divided by a quadratic polynomial. Our divisor here now is what? Is quadratic. Let's try and use x squared plus x minus 6. Okay, now here we have our p to be what? Minus 1, and we have our q to be what? 6. Look at this. We said something earlier. We said that this p of x can be written as p of x is equal to q of x multiplied by a quadratic polynomial. We said that p of x can be written as product of 2 polynomials, of which one of them is quadratic. Now, we can find what is q of x by saying p of x divided by q of x. We can find what? Q of x by saying p of x divided by q of x. Now, just look at it now. We have p of x is equal to q of x multiplied by the quadratic polynomial. And then we say that if you want to find what will be your quotient, which is your q of x, divide both sides by the quadratic polynomial. That means dividing both sides by quadratic polynomial, we're going to have p of x divided by the quadratic polynomial, which is x squared minus px minus q. And then we say, let's use, for instance, let this our quadratic polynomial, let it be x squared plus x minus 6. So when you compare this quadratic polynomial, this standard form of quadratic polynomial that we say x squared minus px minus q, comparing it with this polynomial we want to use now, which is x squared plus x minus 6, what are you going to have? We will see that p is minus 1 and q is 6. Now, and we say we can use synthetic division to find what the quotient is going to be. Are we together? Yes. So when we try it, look at what we're going to have. We're going to have minus 1 and then 6, which is our p and q. So here we're going to use the coefficient as usual. Now, let's go. Let's see how we do this. You see this one, we bring it down. So this one multiplied by p, which is minus 1, is going to give you minus 1. Now this minus 1, then add it together with what is above, which is minus 8. So here we have minus 8 minus 1. It's going to give you minus 9, right? Good. We write minus 9 down. Then this minus 9 multiplied by your p is going to give you 9. Now let's step backward to 1. So this one multiplied by q, we're going to write it under 9. So it's going to give you 6. So 1 multiplied by q, and q is what? Is 6. So that means we are going to have 6. So here we have minus 72 plus 9 plus 6. It's going to give us minus 57. Are we together? Yes. So here we have minus 57 multiplied by p, which is minus 1, is going to give us 57, right? Good. Let's step backward again. We have minus 9. So this minus 9 multiplied by q, and q is 6, is going to give us minus 54. Let's add up everything. That means we say 382 plus 57 minus 54 is going to give us 385. This 385 multiplied by our p, which is minus 1, is going to give us minus 385. Let's step backward to minus 57. This minus 57 multiplied by q, and q is 6, is going to give us minus 342. Let's add up everything. 727 minus 385 minus 342 is going to give you 0. So this 0 now multiplied by p, which is minus 1, is going to give you 0. Let's step backward to 385. 385 multiplied by q, and q is 6, is going to give us 2310. Let's add up everything. Minus 2310 plus 0 plus 2310 is going to give us 0. Are we together? So here we see that we use synthetic division to find q of x. Okay, when you write a polynomial as a product of two polynomials, like q of x and quadratic polynomials, so you can use your polynomial divided by the quadratic polynomial to get your q of x. Are we together? So, and then we say that we can use synthetic division, and this is how we use synthetic division. Not only that, you can also do it directly using long division. You can also do it using what? Long division. Yes, you can use long division and it will still give you the same thing. So when you use long division, it will still give you the same thing. Now look at what we have here. We said that q of x is equal to what? X cubed minus 9x squared minus 57x plus 385. Now a question is, why did we have x cubed? Now look at it. We have a polynomial of degree 5. When it's being divided by a quadratic polynomial, and you know that quadratic polynomial is of degree 2, so it's going to reduce the 5 by 2. So when you reduce 5 by 2, it's going to give you what? 3. So that is why we have q of x to be a polynomial of degree 3. Okay, so when you say q of x is now x cubed minus 9x squared minus 57x plus 385. Are we together? Yes. And then we see here that remainder is what? Is 0. Now let's go. This one is just a basic understanding before we go fully into what we call Bairstow's method. Now, what do we understand by Bairstow's method? Bairstow's method is a numerical method that we can use to find the root of polynomials of higher degrees. Okay? Like from degree 3, 4, 5, 6, 7, 8, and so forth. Even though it's going to take time to find it, but you are going to find what you are looking for using Bairstow's method. So now look at this. Bairstow's method, the idea is that we're going to use Bairstow's method to extract quadratic polynomial from a polynomial you have. Hello. Bairstow's method gives us the idea of how to extract quadratic polynomial from the polynomial you have. Let's say you have a polynomial of degree 3. When you have a polynomial of degree 3 and you want to solve it using Bairstow's method, Bairstow's method will extract quadratic polynomial from this polynomial of degree 3. That means we are going to have polynomial of degree 1 and polynomial of degree 2. That is quadratic polynomial and linear polynomial. And I'm very sure you know how to solve linear polynomial. It's very simple. You can find the root, right? And then quadratic polynomial, very simple. You know how to find the root. That is it. So the idea is when you have a polynomial of any degree, Bairstow's method helps you to break it down into quadratic polynomials or into product of quadratic polynomial. It will first of all extract quadratic polynomial from the polynomial that is given to you. Now, when you extract this quadratic polynomial, you can find the root of the quadratic polynomial. And if your Q of x is still of higher degree, you can also apply Bairstow's method again to extract more quadratic polynomials from your Q of x that you have, and then thereby you split them and you solve. Very simple. Now let's see what we are trying to say. Bairstow's method will help you to extract a quadratic polynomial. Let's see, x squared minus p of x minus q from the p of x that is given to you, such a way that it will leave a remainder 0. In such a way that it will do what? It will leave a remainder 0. So the Bairstow's method is not just extracting quadratic polynomial, no, but quadratic polynomial that when you say p of x divided by this quadratic polynomial is going to leave a remainder 0. Yes, it's going to leave a what? A remainder 0. That is the idea. And then for this quadratic polynomial to leave a remainder 0, it depends on the value of p and q. I think you agree with me. Yes, it will depend on the what? On the value of p and q. So Bairstow's method, we extract this quadratic polynomial x squared minus px minus q, and it will give us the value of p and q in such a way that when you perform either long division or synthetic division, like p of x divided by this your quadratic polynomial, the remainder will be what? Will be 0. Now let's take a close look at this synthetic division here, where we used p is equal to minus 1 and p is equal to 6. Now when you look at it, this last one we just did now, where we use x squared plus x minus 6, we see that when we did, what happened? It gives us remainder what? 0. So that is to say p and q has to be what? A specific number before it will give you remainder 0. Let's say for instance your p is 2 and your q is 3. When you perform the division, the remainder is not going to be 0. Yes, the remainder is not going to be what? It's not going to be 0. Are we together? Like for instance now, before you use p equal to 2 and q is equal to 3, that means you are trying to use this quadratic polynomial. s squared minus 2x minus 3, right? S squared minus 2s minus 3. Now, when you try to use p of x divided by this s squared minus 2s minus 3, it's not going to give you zero remainder. Are we together? Good. So we are saying that Bairstow's method will help us to extract quadratic polynomial from the p of x in such a way that when you say p of x now divided by this extracted quadratic polynomial, the remainder is going to be what? 0. And then you discover that you're going to have a quotient and the remainder 0. Are we together? Yes. Now let's go. The question is, how can you find this p and q to make x squared minus px minus q a factor of p of x in such a way that when you divide it by the p of x, or when you say p of x divided by this quadratic polynomial, the remainder is going to be 0. How can we do it? Now look at this. Let me show you something from a synthetic division, because this Bairstow's method, we make use of two popular methods that we know, which is synthetic division. We make use of synthetic division and we make use of Newton-Raphson. Now, synthetic division, let me give you a clue. This is a standard form of a polynomial. P of x is equal to a naught x raised to the power of n plus a1, x raised to the power of n minus 1 plus a2, x raised to the power of n minus 2 plus a n minus 1x plus an. So this is a standard form of a polynomial. So when we want to use a synthetic division, you see the table, right? We are using the coefficient of this polynomial, and the coefficient is a naught, a1, a2, a3 to an. Are we together? To an. And then we are going to use our divisors to be p and q. P and what? And q. Now, when we arrange it like this, pay attention. We first of all bring down this a naught. Okay? So when we perform what we do, below this line is going to be the result, right? Below the line is going to be the result, and the result is going to be b naught, right? B is going to be what? B. Now look at this. In the first row we have what? A naught. Second row we are going to have what? The multiplication, right? And then you see this line. So the line is the result. Now let me show you something. We bring down a naught and it becomes b naught, right? Good. Now we say this b naught multiplied by p is going to give you p b naught. When you add a1 and p b naught, the result is going to give you b1. The result should be what? Or let's say we call the result b1. Or the result, it should be variables of b. Are we together? Good. Now this b1 multiplied by p is going to give you p b1. We step back to b naught. B naught multiplied by q is going to give you q b naught. Now we continue like this until when we see bn minus 2 multiplied by p is going to give you p bn minus 2, and then we step back again to bn minus 3. Bn minus 3 multiplied by q is going to give you q bn minus 3. When we add an minus 1 plus p bn minus 2 plus q bn minus 3, it's going to give you bn minus 1. And then the last one also. Now, if you look at it very well, you see that bn is the sum of an plus pbn minus 1 plus qbn minus 2. And bn minus 1 is the sum of an minus 1 plus pbn minus 2 and qbn minus 3. Are we together? Good. Now look at this. Look at this. You know, when you are using a synthetic division to break down a polynomial, right? It's going to reduce the power, right? depending on your divisor, the degree of your divisor, right? Good. Now let's go. Look at it again. Here we have Bn is equal to An plus Pbn minus 1 plus Qbn minus 2. So when you generalize it, it's going to be Bi is equal to Ai plus Pbi minus 1 plus Qbi minus 2. Okay? So that means this is the quotient. The quotient Q of S is going to be B naught xn minus 2 plus B1 xn minus 3 plus so Bn minus 3x plus Bn minus 2. Hello. When you say P of x divided by any polynomial, let's say of degree 1, we are going to, your result is going to be reduced by degree 1, and then we say the result is what? Is Q of x. So this Q of x now, to differentiate it from the P of x that you have, and then we see that we are using A to stand for the coefficient of P of x. So since we perform a synthetic division to get Q of x, we use B to represent the coefficient of the result now. And when we perform this again, when we perform the synthetic division again, we are going to have C to represent the coefficient of the extracted quotient that we're going to have. Now look at what I'm trying to say. If you perform another operation again, that is, look at what you have. You have B naught, B1, B2 to Bn, and then you have your Q and B. Bring down your B. When you bring it down, the product or the result you are going to have, we say let's use C to stand for the coefficient of what we are going to obtain, right? Good. So here we bring it down, it becomes C naught, right? So when you say C naught multiplied by P, it's going to give you PC naught. When you add B1 plus PC naught, it should give you C1. This C1 multiplied by P is going to give you PC1. Let's step back to C naught. C naught multiplied by Q is going to give you QC naught. You continue like this until you get Cn is going to be the sum of Bn plus Pcn minus 1 plus Qcn minus 2. And then Cn minus 1 is the sum of Bn minus 1 plus Pcn minus 2 plus Qcn minus 3. Are we together? Yes. Now let's go. When we are talking about this Bairstow's method, we are actually looking at the value of P and Q in the extracted quadratic polynomial, such that when P of x divided by this quadratic polynomial that you extract is going to give you remainder 0. Okay? Now, this synthetic division we did now, we'll call it our iteration. That is what we are going to be doing. And any successful iteration, there is things we are going to do, right, to finish the iteration. So for us to finish the iteration, or we say for each iteration, we are going to have new P. We are looking for P and Q, right? Such that the P of x divided by this quadratic polynomial is going to give you 0, right? And we are going to have a starter P. And when we perform the first one, we are going to get new P. So the new P we are going to get is going to be P that you already have plus delta P. Are we together? And then the new Q that you're going to have is going to be the Q you already have plus delta Q. Okay? So the problem now is, how can we get this delta P and delta Q? Don't be afraid. We are not going to perform any derivative. Okay? Good. But I'm going to show you a very simple formula we are going to use. I'm going to give you a very simple formula that applies for polynomial of any degree. Okay? So for polynomial of any degree, you are going to have Cn minus 1 delta P plus Cn minus 2 delta Q is equal to minus Bn. Look at it. Look at the structure. Delta P, delta Q. We start from Cn minus 1. The next one, Cn minus 2 is equal to minus Bn. We say Cn minus 1 delta P plus Cn minus 2 delta Q is equal to minus Bn. Now the next one, we continue with Cn minus 2 delta P plus Cn minus 3 delta Q is equal to minus Bn minus 1. Hello, we make use of Cn minus 1, Cn minus 2, and Cn minus 3. And then also Bn and Bn minus 1. So this formula is for polynomial of any degree. It's for polynomial of what? Any degree. Now look at this very well. When you have Cn minus 1 delta P plus Cn minus 2 delta Q is equal to minus Bn, and then this one equation, and then another equation, Cn minus 2 delta P plus Cn minus 3 delta Q is equal to minus Bn minus 1. This is another equation, and these two equations are related. So we can solve this simultaneously. You can solve these two equations simultaneously to obtain your delta P and delta Q. So if you don't want to use simultaneous linear equation, okay, you can use metrics to solve. And using metrics, that is where you will see some kind of formulas, okay. Now I'm going to use metrics to show you some formulas you're going to see in any material you want to use, okay. So depending on the choice you want to use. So but if you want to use this one, it takes a whole lot of time. So but when you just figured out this formula, the best thing for you to do, I think, is just to use simultaneous linear equations. Okay, use simultaneous linear equation, you can find your delta P and your delta Q. But perhaps for knowing sake, you want to still explore many other possible solutions. Okay, now look at this. You first of all write or present these two equations in matrix form. You present it in matrix form, and I'm very sure you know how to write it in matrix form. It's going to be like this: Cn minus 1, Cn minus 2, Cn minus 2, Cn minus 3. This is 2 by 2 matrix, and then we have another matrix, delta P and delta Q is equal to our resultant minus Bn and minus Bn minus 1. Are we together? Yes. Now, from here now, let's solve. Under this one, maybe some people can say Cramer's rule or determinant rule or whatsoever, okay? But you know that. Now let's look at this. From this matrix now, let's have different matrix again. Let's have matrix A. Matrix A is your default matrix, which is Cn minus 1, Cn minus 2, Cn minus 2, Cn minus 3. 2 by 2 matrix, okay? Now, let's go further to find the determinant of this matrix. So when you want to find the determinant of this matrix, you know, the leading diagonal minus the minor diagonal. That is, you see Cn minus 1 multiplied by Cn minus 3 minus the minor diagonal, which is Cn minus 2 multiplied by Cn minus 2. So when you say Cn minus 2 multiplied by Cn minus 2, it's still the same thing. That means you can say Cn minus 2 squared, in bracket squared, right? Good. So this is for A, matrix A, right? Now let's form another matrix. Let's decide to give it a name, matrix AP. Matrix what? AP. So this matrix AP, we're going to interchange the first column. Interchange the what? The first column with our resultant. The resultant is minus Bn and minus Bn minus 1. So, and then our first column is Cn minus 1 and Cn minus 2. So when we interchange it, we are going to have minus Bn, that is the first column now, and then minus Bn minus 1. Then the second column remains unchanged, which is Cn minus 2 and Cn minus 3. So again, let's find the determinant of this matrix AP. So the determinant of this matrix AP, as usual, the leading diagonal minus the minor diagonal, which is minus Bn multiplied by Cn minus 3 minus, we have minus Bn minus 1 multiplied by Cn minus 2. It's going to give you plus. So therefore, the determinant is going to be minus Bn multiplied by Cn minus 3 plus Bn minus 1 multiplied by Cn minus 2. Are we together? Yes. Now let's form the last matrix. Let's call this matrix AQ. Let's call it what? Matrix AQ. So matrix AQ, we are going to interchange the second column with the what? The resultant, or with the result. What is our result? Minus Bn and minus Bn minus 1 is going to replace the first column. What is the first column? Cn minus 2 and Cn minus 3. So in place of Cn minus 2 and Cn minus 3, which is the second column, we're going to write minus Bn and minus Bn minus 1. Now let's again go further and find the determinant of this matrix AQ. So the determinant is going to be minus Bn minus 1 multiplied by Cn minus 1 plus Bn multiplied by Cn minus 2. Hello. I think you understand this, right? Good. So now, for us to find the value for delta P and delta Q using matrix, we are going to say that the determinant of matrix delta P all over the determinant of matrix A. And then, what do we say that the determinant of matrix AP is? We say minus Bn multiplied by Cn minus 3 plus Bn minus 1 multiplied by Cn minus 2 all over the determinant of matrix A, which is Cn minus 1 multiplied by Cn minus 3 minus Cn minus 2 squared. So when you perform this, it's going to give you the value for delta P. Now let's go for delta Q. The value for delta Q is going to be the determinant of the matrix AQ all over the determinant of matrix A. What is the determinant of matrix AQ? Is minus Bn minus 1 multiplied by Cn minus 1 plus Bn multiplied by Cn minus 2 all over Cn minus 1 multiplied by Cn minus 3 minus Cn minus 2 all in bracket squared. Hello. Are we together? So when you continue this iteration, you know, this is what we call iteration, right? You perform synthetic division. From synthetic division, you are going to get new P. And what do you say that new P is going to be? It's going to be the P that you have plus delta P. You are going to get new Q. What is going to be your new Q? Is the old Q that you have plus delta Q. So when you get this, how can you get delta P and delta Q? I showed you how to get delta P and how to get delta Q, right? Good. So when you perform this and get new P and new Q, you have performed what we call first iteration. You've performed what we call what? The first iteration. So now, when you continue this iteration, how will you know when to stop? What is the criteria to know when to stop your iteration? Now, we use the criteria what we called approximate error. Okay, there is what we call what? Approximate error on P and Q. So when this approximate error is just as nothing or 0, that is where we'll stop. Are we together? Now look at it. We see it. We have what we call approximate error on P and Q, right? This will help us to determine when to stop the iteration. What is this approximate error? Approximate error is like this. It's given us the modulus or the absolute value of delta P all over P. The absolute value of delta P all over P multiplied by 100%. Are we together? The approximate error on P can be given as the absolute value of delta P all over P multiplied by 100%. And then also the approximate error on Q is the absolute value of delta Q all over Q multiplied by 100. The absolute value of delta Q all over Q multiplied by 100%. So this is what we call the approximate error. So when this approximate error is very small, like it's almost nothing, that is when we stop the iteration. Okay, so we said when this tolerance is reached, when it is very Good to neglect, right? Doesn't have any meaning or it doesn't add any value. So we say that the estimated coefficient of P and Q, what you have as of P and Q, when you reach this uh, tolerance, okay, when you reach this level where your approximate error on P and Q is very, very small, so your P and Q will be used to find the what? The root of the quadratic polynomial that you extracted. Now, when we are talking about Bairstow's method will extract a quadratic polynomial of the form x squared minus px minus q. So this still Bairstow's method we continue to solve until we find the value of p and the value of q such that when you say p of x divided by this extracted quadratic polynomial and having this p and q, the remainder is going to be what? 0. Okay, that means we have a quadratic polynomial. Now when we get this p and q such that it qualifies the requirement, okay, that means we have a formula that we can use to find the root of this quadratic polynomial. Yes, you can solve the quadratic polynomial. Yes, I'm very sure you know how to solve it. Yes, you can solve it any method you want. You can use quadratic method to solve it. You can use factorization. You can use completing the square. Okay, but if you don't want to go all of that, even here we have our own formula we can use. What is our formula? We say x is equal to p plus or minus square root of p squared plus 4q all over 2. 4q all over 2. Are we together? Yes. When you have gotten your p and q, when this tolerance is reached, you use this formula x is equal to p plus or minus square root of p squared plus 4q all over 2 to find the root of the extracted polynomial. If you don't want to use this one, there is no problem. You can just go ahead and solve your quadratic polynomial that you just extracted. Are we together? So now maybe you are asking at this point, we are using, okay, maybe you are asking how do we get this formula? Okay, let me show you how we get this formula. Okay, now look at this. At this point, we are trying to use Bairstow's method to extract a quadratic polynomial from p of x. And the extracted quadratic polynomial that we want is what? S squared minus ps minus q, right? And we get to a point that we are okay with p and q that we obtained. So we use this formula to find the root of the extracted quadratic polynomial. Okay, we use a formula to do or to find it, and I said you can use any formula you write, okay, which is x is equal to p plus or minus square root of p squared plus 4q all over 2. Maybe you are asking, how do we come about this formula? It's very common. We get this formula from a quadratic formula. Okay, now remember, we are talking about the extracted quadratic polynomial to be x squared minus px minus q, right? Yes, and we say we want to find the root of this extracted polynomial, right? And then we see that this extracted polynomial is just like a quadratic equation. How do we recognize a quadratic equation or quadratic polynomial? It's like this: ax squared plus bx plus c, isn't it? Yes. And when you want to solve this quadratic equation or quadratic polynomial, how do you do it? You have a quadratic method where we say x is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. I think this is true, right? Yes. So now, when you look at these two equations, the extracted polynomial we want to get, and then the standard form of quadratic polynomial, comparing two of them, you can see that a is 1 and b is minus p and c is minus q. Is that true? Let's try to use this quadratic method to solve the extracted polynomial. Let's try it. So that means we have x is equal to minus, where we say minus b plus or minus square root of b square minus 4ac all over 2a. Let's solve it. We know the value of a, we know the value of b, we know the value of c, right? Let's go. We say that x is equal to minus, open bracket, minus p plus or minus square root of minus p squared minus 4 times our a is what? 1, and then our c is minus q all over 2a. Our a is 1, then we have 2 times 1. Now look at it. We have x is equal to, when you say minus times minus p, it's going to give you minus, it's going to give you positive p, right? Then we have our plus or minus square root of, inside where we have minus p squared, is going to give you p squared. Then we have minus, when you say 4 times 1 is 4, then 4 times minus q is going to give you minus q, then multiply by the minus outside, it's going to give you plus 4q all over 2. So this is how we come about the root of the extracted polynomials. Are we together? Yes. Now let's go. Let's pick a problem and solve under this Bairstow's method. You know, all we've been doing is just a basic understanding of Bairstow's method. Okay, from the elementaries, the basics, and all of that, for you to understand Bairstow's method. Let's take a look at this question. Look at this. Look at this. We are asked to use Bairstow's method to extract a quadratic polynomial and then hence solve. Okay, look at this. We have p of x is equal to x raised to the power of 4 minus 5x cubed plus 10x squared minus 10x plus 4. Okay, in this case, our polynomial is of degree what? Degree 4. Degree 4. Now we are given p and q, an estimated error. Our p is what? Our p is 0.5 and our q is minus 0.5. Estimated error is 0.01. Very small. Are we together? Good. So look at it. We've been saying what Bairstow's method is all about. For us to solve this polynomial such that this polynomial is equal to 0, we are going to have what we call 4 possible roots of this polynomial. This is polynomial of degree 4. So we are expecting 4 values of x. There are 4 values of x that will satisfy this polynomial. Are we together? So how can we find all the root of this polynomial? Now we are using Bairstow's method. Bairstow's method said the first step is to extract a quadratic polynomial from this polynomial of degree 4. When you extract it, we are going to have a product of 2 polynomials. Since this one is polynomial of degree 4, when you extract a quadratic polynomial, it's going to be product of 2 quadratic polynomials. Hello? Yes, it's going to be product of 2 quadratic polynomials. And then you remember the beauty of this Bairstow's method is that the extracted quadratic polynomial, when you say p of x divided by this extracted quadratic polynomial, the remainder should be 0. Okay, so that is what we want to do. Now pay attention using Bairstow's method. Let's go. First iteration, using synthetic division. Using what? Synthetic division. Now, you know, we say we are going to use the what? The coefficient of our p of x. The coefficient of our p of x. And then the coefficient is 1, we have minus 5, we have 10, we have minus 10, and we have 4, right? That's the coefficient. And then we pay attention and see that there is no any missing term. There's no missing term. So we have our p and we have our q. Let's arrange it. P and q. P and q. Now let's go. You see this one, we bring it down. So this one multiply by p. And p is 0.5. It's going to give you 0.5. Then we add together. We say minus 5 plus 0.5. It's going to give us minus 4.5. Are we together? Yes. So this result, which is minus 4.5, multiply by p again, is going to give you minus 2.25. All right. Now we step back to 1. This one multiply by q. Q is minus 0.5. It's going to give you minus 0.5. Okay, so we add up everything. What are we adding up? 10 and minus 2.25 and minus 0.25. When we add it together, it's going to give us 7.25. Are we good? Yes. So this 7.25 multiplied by p is 0.5. It's going to give you 3.625. Okay, we step backward again to minus 4.5. Minus 4.5 multiplied by q is minus 0.5. It's going to give you 2.25. We add up. We say minus 10 plus 3.625 plus 2.25 is going to give us minus 4.125. Are we together? Yes. Now again, this minus 4.125 multiplied by p, which is 0.5, is going to give us minus 2.0625. And then we step backward to 7.25 multiplied by q is going to give us minus 3.625. We add up again, that is 4 plus minus 2.0625 plus minus 3.625. When we add up, it's going to give us minus 1.6875. Are we together? Yes. Now let's go. This result we have here now, let's give it a name. The last one here is Bn. The next one is going to be Bn minus 1. The next one is going to be Bn minus 2. The next one is going to be Bn minus 3, and so forth. But the last one here is Bn, followed by Bn minus 1, followed by Bn minus 2, followed by Bn minus 3, so forth. Are we together? Yes. Now let's go again. We perform another operation. We bring down the P and Q. Now this one here, we bring it down again. This one multiplied by P, which is 0.5, is going to give us 0.5, right? Good, we add up, that is minus 4.5 plus 0.5. It's going to give us minus 4. Then this minus 4 multiplied by P again, it's going to give us minus 2. Then we step backward to 1, multiplied by 0 minus 0.5, it's going to give us minus 0.5. We add up. What are we adding up? 7.25 plus minus 2 plus minus 0.5. Add up is going to give us 4.75. So this 4.75 multiplied by P, which is 0.5, is going to give you 2.375. Then we step back to 4, to minus 4. So minus 4 multiplied by Q, which is minus 0.5, is going to give us minus 2. Sorry, it's going to give us positive 2. Now we add up. We say minus 4.125 plus 2.375 plus 2 is going to give us 0.25. We can stop here. Hello? We can do what? We can stop here, because anything we are going to do again, we don't need it. Okay? So, but you remember, that column is going to be our Cn, then followed by Cn minus 1, followed by Cn minus 2, followed by Cn minus 3, and so forth. Are we together? Yes. Now, using this table, look at the formula that we have. We say Cn minus 1 delta P plus Cn minus 2 delta Q is equal to minus Bn. And then that is equation number 1. Another equation, Cn minus 2 delta P plus Cn minus 3 delta Q is equal to minus Bn minus 1. So this is two simultaneous linear equations. So now let's look at the table. From the table, what is Cn minus 1? Cn minus 1 is 0.25. So we have 0.25 delta P. Alright? Plus, what is Cn minus 2? Cn minus 2 is 4.75. So here we have 4.75 delta Q is equal to, we have minus Bn. What is Bn? Bn is minus 1.6875. So minus is going to give you positive. So we're going to have 1.6875. This is equation 1. Let's go to equation 2, which is Cn minus 2 delta P plus Cn minus 3 delta Q is equal to minus Bn minus 1. Look at it again. Cn minus 2 is 4.75. Then minus, we have Cn minus 3 is minus 4. So here we have minus 4 delta Q is equal to, what is Bn minus 1? Bn minus 1 is minus 4.125. So here minus is going to give us plus. So here we have 4.125. So from these two equations, we can solve for delta P and delta Q. using any method of your choice. So using any method of your choice, we are going to see that delta P is equal to 1.1180 and delta Q is 0.2964. Are we together? Yes. Now you remember we say we are going to obtain new P and new Q. So what is our new P? New P is going to be the P that we already have plus the change of P or delta P that we just obtained is going to give us the new P. And then what about Q? It's going to be the Q that we already have plus the delta Q we just obtained. Now let's go. The P we already have is 0.5 plus the delta P we obtain is 1.1180, right? When we add it together, it's going to give you 1.618. That is the new P. Now, what about Q? Q is going to be minus 0.5 plus 0.2964. Okay? That is 0.2964 is the delta Q, right? When we add together, it's going to be minus 0.2036. Minus 0.2036. Are we together? Yes. Now let's go. Let's go. Our approximate error. Approximate error on P and Q. So approximate error, we say the absolute value of delta P all over P. And then the P we are talking about is the new P. The new P. So the delta P is 1.1180 all over the new P, which is 1.6180, multiplied by 100%. So when we multiply this, it's going to give us 69.0977%. You can see it still is very high. We cannot neglect this. Now let's go again. Approximate error on Q. The absolute value of delta Q all over Q times 100. And then here we have 0.2964 all over minus 0.2036 multiplied by 100, which is equal to 145.5796%. You see that this is very high. So we have performed first iteration. We perform what? First iteration. Let's go to second iteration. Second iteration using the same P of X and the new P and the new Q that we obtained. Okay, good. Look at it. We have the table. We perform the operation. So when you perform the operation, this is what you are going to have. Okay, as you have this, you know your Bn, you know your Bn minus 1, you know your Cn, you know your Cn minus 1, you know your Cn minus 2, you know your Cn minus 3. Are we together? Yes. From the table, you can come up with your formula, which is Cn minus 1 delta P plus Cn minus 2 delta Q, which is equal to minus Bn. Okay, and then this is equation 1. Equation 2, Cn minus 2 delta P plus Cn minus 3 delta Q, which is equal to minus Bn minus 1. So from the table, you see that Cn minus 1 is 0.0939 delta P, okay, plus your Cn minus 2 is 1.2665, right? Then we have delta Q is equal to Bn, we have 0.6255, right? Good. And then this is equation 1. Then the second equation, Cn minus 2 delta P, we have 1.2665 delta P minus 1.764 delta Q, which is equal to 2.3146. So solving this equation, or solving for changing delta P and delta Q in these two equations, we see that delta P is equal to 2.2799 and delta Q is 0.3245. Are we together? Yes. So, in each iteration, you obtain new P. So, what is the new P? The new P is the previous P that you have, that is the recent P that you had, plus the delta P that you obtain now. And then your new Q is going to be the Q that you already have, plus the delta Q that you just obtained. So here we have new P is going to be 1.618, which is the previous P, plus the delta P that you have, which is 2.2799. Now when you add this together, it's going to give you 3.917. And then for Q, the new Q is going to be the previous q that we have, which is minus 0.2036 plus the delta q, which is 0.3245, is going to give you 0.1212. Are we together? Now we perform the approximate error. So performing the approximate error, which is approximate error on P and approximate error on Q, absolute value of delta P all over P multiplied by 100. That is for approximate error on P. So here we have 2.2799 all over 3.917 multiplied by 100, which is going to give us 58.2053%. And then for the approximate error on Q, which is the absolute value of delta Q all over Q multiplied by 100. So here we have 0.3248 all over 0.1212 multiplied by 100, which is going to give us 267.9868. Are we together? Yes. So here we have performed the first iteration, we perform the second iteration, and then the tolerance have not been reached. Okay, the criteria, the approximate error that we are given to know when to stop, we have not reached. Okay, so we continue to do the iteration. We continue to do the iteration, until the approximate error is reached, okay, or the level of tolerance is reached. So we are going to perform this iteration up to 10 times, okay. So from the 10th time, I think we are going to get new P to be 3 and new Q to be minus 2. Hello. We are going to get new P to be 3 and new Q to be what? Minus 2. With the approximate error on P to be 0.01 and the approximate error on Q to be 0.01 also. So when we've gotten to this level, you know that we want to extract a quadratic polynomial in this form, x squared minus px minus q, okay, such that when p of x is divided by this quadratic polynomial, the remainder is going to be 0, right? Good. And we say we solved and we obtain p to be what? To be 3 and the q to be what? Minus 2. Isn't it? Yes. Good. Now look at it. Comparing this now, you know, the extracted polynomial that we're looking for is s squared minus ps minus q. And here we have p is equal to 3 and q is equal to minus 2. Let's substitute it inside. When you substitute it, what are you going to have? You are going to have that x squared minus 3x plus 2 is equal to 0. Hello. So this is the extracted polynomial that we want. Extracted polynomial that we are what? That we are looking for. Yes. Now, this is the extracted polynomial. You can solve this polynomial. You can solve this quadratic equation using any method of your choice. You can use factorization method. You can use completing the squared. You can use quadratic method. You can use anyone. Or let's use the method that we used here. The formula that we found out here. Now let's, our formula say x is equal to p plus or minus square root of p squared plus 4q all over 2. Here we have p is 3 and q is minus 2. So when you substitute, you're going to have x is equal to 3 plus or minus square root of 3 squared plus 4 open bracket minus 2 all over 2. Are we together? Yes. So here we're going to have x is equal to 3 plus or minus square root of 3 squared is 9. Now we have 4 times minus 2 is going to give us minus 8. So here we have 9 minus 8, which is equal to square root of 1, which is equal to 1. So here we have 3 plus or minus square root of 1 all over 2. Now we say plus or minus, so we split it together. We split it into 2. So one is going to have plus or minus. So here we have x is equal to 3 plus 1 all over 2 or 3 minus 1 all over 2. So when you say 3 plus 1, it's going to give you 4 all over 2, or 3 minus 1 is going to give you 2 all over 2. So here we have x is equal to 2 or x is equal to 1. So this is the solution to the extracted quadratic polynomial. You can use your method. You can use factorization method. You can use quadratic method to find these roots of this extracted polynomial. Are we together? Yes. Now look at this. we are looking at solving this polynomial of degree 4, which is s raised to the power of 4 minus 5x cubed plus 10x squared minus 10x plus 4, right? And then Bairstow's method say that is going to help us to extract a quadratic polynomial, and it have done so by giving us this x squared minus 3x plus 2, which is equal to 0, and we solve this one. So the question is, how can we, look at this guy. P of s is equal to q of x multiplied by the quadratic polynomial. So, and we said if you want to find the q of x, you say p of x divided by the quadratic polynomial. And then we say you can use any method. You can use long division and you can use synthetic division. Hello. You can use what? Long division, and you can use what? Synthetic division to find the product of two polynomials, of which one of them is the extracted quadratic polynomial, such that when you multiply these two polynomials, it's going to give you your p of x. So we say we can use any of these two methods. You can use long division and you can use synthetic division. Are we together? So when you are using synthetic division, you look for p and q. P and q. Are we together? And then you know that your p is what? P is 3 and q is minus 2. So you can use the table and extract it. Or you want to use long division. Look at long division here. So if you want to use long division, so look at it. You use your long division, look at it, perform it like this. So please, if you are not clear enough on how to use this long division, you can use your synthetic division. We have videos on synthetic division and we have videos on long division. All right, yes, because I don't want this video to take us too long, and it has already taken us too long. So when you use either synthetic division or long division to find q of x, we are going to see that the p of x that we have, which is x raised to the power of 4 minus 5x cubed plus 10x squared minus 10x plus 4, is the product of two quadratic polynomials, of which one of them is Bairstow's method that help us to extract it. Hello. Bairstow's method help us to extract this x squared minus 3x plus 2. Then we perform long division or synthetic division to find the remaining one, which is x squared minus 2x plus 2. So from here, we have two quadratic polynomials, and I'm very sure you know how to solve for the root of these two quadratic polynomials. So when you solve for them, you obtain their root. So how? It is Bairstow's method that helps you to do it. So for these first polynomials, when you solve it, the root is what? 2 or 1. And then for the second polynomial or quadratic equation, the root is what? 1 minus I or 1 plus I. Hello. So therefore, we see that we use Bairstow's method and we solve for the root of this polynomial of degree 4. And the root is what? 2 or 1 or I minus 1 minus I or 1 plus I. Yes. Thank you very much for watching. This is a wonderful video on Bairstow's method. I don't know if you like it. If you like it, please you can give us a thumbs up. And if you are new to our YouTube channel, please I want you to like our videos, subscribe if you have not, and share our videos. Okay? Yes, we are dedicated in giving you a very simple, well-detailed, explained maths lessons. Yes. Let's take more examples on numerical method and other topics or other subjects. Yes. Thank you for watching. Stay blessed. Thank you.